Okay, so we want to talk about MOSFETs now. So a MOSFET is a different type of transistor, similar to, but a little bit different than the BJT. So first of all, here is the MOSFET page in Wikipedia that shows all of this. But it's interesting that in Wikipedia, it said it's the basic building block of modern electronics, and there is an estimated 13 sextillion 1.3 times 10 to the 22nd MOSFETs that have been manufactured between 1960 and 2018. So that is a lot of MOSFETs. So there's a lot more MOSFETs than BJTs that are made. So the traditional metal oxide semiconductor, which is your MOS, right? That's the MOS of the MOSFET structure, is obtained by growing a layer of silicon dioxide on top of a silicon substrate. Okay, so what in the heck does all that mean? Okay, so let's go look at what a MOSFET looks like. So here is a MOSFET. So it has an N region, an N region, and then it's grown with a P region in between. So it looks a lot like an NPN region, except for in this case, the connection to that middle region is insulated. So it's insulated by an oxide. So it has a complete insulator separated between the two, where with the BJT, this insulator was out and we made contact to that middle P region. Okay, so we need to look at operating regimes on how this works. So let's go here and look. Okay, so here is your basic MOSFET. So I have an N region, a P region, and an N region. So this is my NPN region. It also connects over to the substrate over here. We don't really care about that. So we're looking right here. So the NPN creates a depletion region, just like we had with the BJT, and then the PN region creates a depletion region over here. So we have two depletion regions, looks like the two back-to-back diodes, just like we had with the BJT. But now I can't make direct connection right here. I only have a capacitor. So what this ends up doing is, if I move over to this figure here, when I put a voltage across here, it's taking and pulling these excess carriers up into this region right here. So what it basically does is creates a channel. So now I create a channel that lets currents flow through here through this channel. The bigger the voltage is, the bigger the channel, the lower the resistance. So if I make a high voltage here, I can create a large channel, and then I can affect how easy it is to flow current from the drain to the source. So you see that this gate region is still my control region. So this is kind of like my base was before to do the control. Okay, so now if I increase this voltage, but eventually when I apply voltages across here between my drain and my source, it kind of changes it, and I get what's called this pinch-off region. So when I get this pinch-off region right here, where this kind of does, then this is going to be like active. So now what's going to end up happening is that the current flow from my drain to my source, it has kind of like this fixed channel. I'm going to get a fixed current through here. So as this voltage changes, so you can kind of see right here, if my drain to source is greater than some value, then my current's kind of fixed. So this region right here is basically the same as active. So this region right here, which is called the ohmic or triode region, is similar to my saturation. And this region here, which is called saturation, is actually my active region. So that gets a little confusing. So we're going to call this one active and this one triode. Okay, let's go and look and put all this together. So let's look at our three regimes. So first of all, cutoff is when my current's about 0. So this has a threshold condition. If my voltage that's applied to the gate is less than my threshold, then there's no current flow. The triode region right here, you see here is my equation. And so what we see here is that this voltage right here is dependent on my gate to source, but also my drain to source. So what ends up happening is that this can be modeled as kind of like a resistor. This is similar to my saturation mode. And then I have this active mode where you see now there's no dependence on VDS. So as my VDS changes, my current is independent. So just to look at the similarities between BJTs and MOSFETs, we renamed the base to the gate, we renamed the collector to the drain, and we renamed the emitter the source. Now we changed these so if someone talks about gate to source, you know they're talking about a MOSFET. So they changed the name so that you can get a better designation of what's a MOSFET. And then if I look at my hybrid pi model, like we had before, so here is the BJT pi model. Here is the MOSFET pi model. So you can kind of see I have the same GRO, I have the same GM VGS. The only difference is now that I have an insulator here, there's no resistor there. So you see that this looks very similar to this. We just dropped off the R pi. So there's no R pi in a MOSFET. Okay, so now that we understand these, let's go and look at LTSpice and look at these plots. So we're going to look at the gate to source first. Okay, so what we're going to be doing is here is our BJT that we had before. And if I'm putting a voltage onto the base emitter, which is my control. So if I look right here as the current as a function of V of my base, you see I end up getting this exponential type relationship. I end up getting some RS, and so it ends up going linear when I get to this point. But we see that this has, here's my 0.7 volt turn on voltage. Okay, so now let's look at the MOSFET. So the MOSFET, let's change this to V of the gate. And you see it looks kind of similar. I got very low current, but it doesn't turn on at 0.7. It turns on at some threshold point. So if I look at this MOSFET here that I'm using, here is my threshold voltage right here. So we have the V threshold is 1.6 volts. So when I get to 1.6 volts, then it starts to conduct up. But you see that that has a similar shape to this one. You know, this one tends to be a little steeper, but you still see I have a turn on voltage and then it goes up. Okay. And the higher my gate to source is, the higher my base to emitter, the more current I get through. Okay, so now we're going to look at my drain to source voltage. So now you see I'm putting in a base emitter voltage and I'm sweeping this. So let's look at this one first. We're going to look at the current as a function of V of C. Okay, so let's kind of review our BJTs. This region right here has a very small dependence on the collector to emitter voltage. So as my collector to emitter voltage doesn't affect my current, it's fairly flat. I have a little bit of slope. That's my early voltage that I had before. And then this region right here is when I hit saturation. So then when I hit that 0.2 volts, you see that my current just drops off because I went into saturation. Okay, now let's go over here and look at our MOSFET. Change this to D for my drain. Okay, and it looks fairly similar. So here is my active regime where I have a small slope. I still have the early voltage, but rather than calling it early voltage, they call it channel length modulation. So instead of using VA, they use 1 over VA, which is called lambda. And then this regime right here is my triode. Okay, and you can kind of see it's a little bit wider than it was for the BJT. So this region right here is a little bit wider, but you see that these shapes look very similar. So most of the stuff that I did with BJTs, I can do with MOSFETs. So when I come in, common emitter amplifier is going to be exactly the same as a common source amplifier. Common collector amplifier is going to be called a common drain amplifier. So like we did before, this is going to become my buffer. This is going to become my main design amplifier. And this is my other amplifier that has a low input impedance, so we don't tend to use it as much. So this is my main amplifier when gain, and this is my